In abstract algebra, ring theory is the study of rings, algebraic structures in which addition and multiplication are defined and have similar properties to those operations defined for the integers. Ring theory studies the structure of rings, their representations, or, in different language, modules, special classes of rings, as well as an array of properties that prove to be of interest both within the theory itself and for its applications, such as homological properties and polynomial identities. Commutative rings are much better understood than non-commutative ones. Algebraic geometry and algebraic number theory, which provide many natural examples of commutative rings, have driven much of the development of commutative ring theory, which is now, under the name of commutative algebra, a major area of modern mathematics. For example, Hilbert's Nullstellensatz is a theorem which is fundamental for algebraic geometry, and is stated and proved in terms of commutative algebra. Similarly, Fermat's last theorem is stated in terms of elementary arithmetic, which is a part of commutative algebra, but its proof involves deep results of both algebraic number theory and algebraic geometry. Non-commutative rings are quite different in flavor, since more unusual behavior can arise, while the theory has developed in its own right. A fairly recent trend has sought to parallel the commutative development by building the theory of certain classes of non-commutative rings in a geometric fashion as if they were rings of functions on non-commutative spaces. This trend started in the 1980s with the development of non-commutative geometry and with the discovery of quantum groups. It has led to a better understanding of non-commutative rings, especially non-commutative Noetherian rings. For the definitions of a ring and basic concepts and the properties, see ring. The definitions of terms used throughout ring theory may be found in the glossary of ring theory. Commutative rings. A ring is called commutative if its multiplication is commutative. Commutative rings resemble familiar number systems, and various definitions for commutative rings are designed to formalize properties of the integers. Commutative rings are also important in algebraic geometry. In commutative ring theory, numbers are often replaced by ideals, and the definition of the prime ideal tries to capture the essence of prime numbers. Integral domains, non-trivial commutative rings where no two non-zero elements multiply to give zero, generalize another property of the integers and serve as the proper realm to study divisibility. Principal ideal domains and integral domains in which every ideal can be generated by a single element, another property shared by the integers. Euclidean domains and integral domains in which the Euclidean algorithm can be carried out. Important examples of commutative rings can be constructed as rings of polynomials and their factor rings. Summary. Euclidean domain equals greater than principal ideal domain equals greater than unique factorization domain equals greater than integral domain equals greater than commutative ring. Algebraic geometry. Algebraic geometry is in many ways the mirror image of commutative algebra. A scheme is built up out of rings in some sense. Alexander Grothendieck gave the decisive definitions of the objects used in algebraic geometry. He defined the spectrum of a commutative ring as the space of prime ideals with Zariski topology, but augments it with a sheaf of rings. To every Zariski open set he assigns a commutative ring, thought of as the ring of polynomial functions, defined on that set. These objects are the affine schemes. A general scheme is then obtained by gluing together several such affine schemes. In analogy to the fact that general varieties can be obtained by gluing together affine varieties. Non-commutative rings. Non-commutative rings resemble rings of matrices in many respects. Following the model of algebraic geometry, attempts have been made recently at defining non-commutative geometry based on non-commutative rings. Non-commutative rings and associative algebras are often studied via their categories of modules. A module over a ring is an abelian group that the ring acts on as a ring of endomorphisms, very much akin to the way fields act on vector spaces. Examples of non-commutative rings are given by rings of square matrices, or more generally by rings of endomorphisms of abelian groups or modules, and by monoid rings. Representation theory. Representation theory is a branch of mathematics that draws heavily on non-commutative rings. It studies abstract algebraic structures by representing their elements as linear transformations of vector spaces, and studies modules over these abstract algebraic structures. In essence, a representation makes an abstract algebraic object more concrete by describing its elements by matrices and the algebraic operations in terms of matrix addition and matrix multiplication, which is non-commutative. The algebraic objects amenable to such a description include groups, associative algebras, and Lie algebras. The most prominent of these is the representation theory of groups, in which elements of a group are represented by invertible matrices in such a way that the group operation is matrix multiplication. Some useful theorems. General isomorphism theorems for rings. Nakayama's lemma. Structural theorems. The Artin-Wedderburn theorem determines the structure of semi-simple rings. The Jacobson density theorem determines the structure of primitive rings. Goldi's theorem determines the structure of semi-prime Goldi rings. The Zariski-Samuel theorem determines the structure of a commutative principal ideal rings. The Hopkins-Levitsky theorem gives necessary and sufficient conditions for a Noetherian ring to be an Artinian ring. Morita theory consists of theorems determining when two rings have equivalent module categories. Wedderburn's little theorem states that finite domains are fields, structures and invariants of rings. Dimension of a commutative ring. The Krull dimension of a commutative ring R is the supremum of the lengths n of all the increasing chains of prime ideals. For example, the polynomial ring over a field K has dimension n. The fundamental theorem in the dimension theory states the following numbers coincide for a Noetherian local ring. The Krull dimension of R, the minimum number of the generators of the primary ideals. The dimension of the graded ring. A commutative ring R is said to be catenary if any pair of prime ideals can be extended to a chain of prime ideals of same finite length such that there is no prime ideal that is strictly contained in two consecutive terms. Practically all Noetherian rings that appear in application are catenary. If is a catenary local integral domain, then, by definition, where is the height of? It is a deep theorem of Ratliff that the converse is also true. If R is an integral domain that is a finitely generated K algebra, then its dimension is the transcendence degree of its field of fractions over K. If S is an integral extension of a commutative ring R, then S and R have the same dimension. Closely related concepts are those of depth and global dimension. In general, if R is a Noetherian local ring, then the depth of R is less than or equal to the dimension of R. When the equality holds, R is called a Cohen-Macaulay ring. A regular local ring is an example of a Cohen-Macaulay ring. It is a theorem of Serre that R is a regular local ring if and only if it has finite global dimension, and in that case the global dimension is the Krull dimension of R. The significance of this is that a global dimension is a homological notion. Morita equivalents. Two rings R, S are said to be Morita equivalent if the category of left modules over R is equivalent to the category of left modules over S. In fact, two commutative rings which are Morita equivalent must be isomorphic, so the notion does not add anything new to the category of commutative rings. However, commutative rings can be Morita equivalent to non-commutative rings, so Morita equivalence is coarser than isomorphism. Morita equivalence is especially important in algebraic topology and functional analysis. Finitely generated projective module over a ring in Picard group. Let R be a commutative ring and the set of isomorphism classes of finitely generated projective modules over R. Let also subsets consisting of those with constant rank n is usually denoted by Pic. It is an abelian group, called the Picard group of R. If R is an integral domain with the field of fractions f of R, then there is an exact sequence of groups, whereas the set of fractional ideals of R. If R is a regular domain, then Pic is precisely the divisor class group of R. For example, if R is a principal ideal domain, then Pic vanishes. In algebraic number theory, R will be taken to be the ring of integers, which is Dedekind and thus regular. It follows that Pic is a finite group that measures the deviation of the ring of integers from being a PID. One can also consider the group completion of this results in a commutative ring K0. Note that K0 equals K0 if two commutative rings are S and Morita equivalent. Structure of non-commutative rings. The structure of a non-commutative ring is more complicated than that of a commutative ring. For example, there exist simple rings, containing no non-trivial proper ideals, which contain non-trivial proper left or right ideals. Various invariants exist for commutative rings, whereas invariants of non-commutative rings are difficult to find. As an example, the nil radical of a ring, the set of all nilpotent elements, need not be an ideal unless the ring is commutative. Specifically, the set of all nilpotent elements in the ring of all nxn matrices over a division ring never forms an ideal, irrespective of the division ring chosen. There are, however, analogues of the nil radical defined for non-commutative rings, that coincide with the nil radical when commutativity is assumed. The concept of the Jacobson radical of a ring, that is, the intersection of all right-left annihilators of simple right-left modules over a ring, is one example. The fact that the Jacobson radical can be viewed as the intersection of all maximal right-left ideals in the ring, shows how the internal structure of the ring is reflected by its modules. It is also a fact that the intersection of all maximal right ideals in a ring is the same as the intersection of all maximal left ideals in the ring. In the context of all rings, whether commutative or non-commutative, non-commutative rings serve as an active area of research due to their ubiquity in mathematics. For instance, the ring of n by n matrices over a field is non-commutative despite its natural occurrence in geometry, physics and many parts of mathematics. More generally, endomorphism rings of abelian groups are rarely commutative, the simplest example being the endomorphism ring of the Klein 4 group. One of the best-known non-commutative rings is the division ring of quaternions. Applications: the ring of integers of a number field. The coordinate ring of an algebraic variety if X is an affine algebraic variety. Then the set of all regular functions on X forms a ring called the coordinate ring of X. For a projective variety, there is an analogous ring called the homogeneous coordinate ring. Those rings are essentially the same things as varieties. They correspond in essentially a unique way. This may be seen via either Hilbert's Nullstellensatz or scheme-theoretic constructions. Ring of invariance. A basic question in the classical invariant theory is to find and study polynomials in the polynomial ring that are invariant, under the action of a finite group G on V. The main example is the ring of symmetric polynomials. Symmetric polynomials are polynomials that are invariant under permutation of variable. The fundamental theorem of symmetric polynomials states that this ring is where are elementary symmetric polynomials. History: commutative ring theory originated in algebraic number theory, algebraic geometry, and invariant theory. Central to the development of these subjects were the rings of integers in algebraic number fields and algebraic function fields, and the rings of polynomials in two or more variables. Non-commutative ring theory began with attempts to extend the complex numbers to various hypercomplex number systems. The genesis of the theories of commutative and non-commutative rings dates back to the early 19th century. while their maturity was achieved only in the third decade of the 20th century. More precisely, William Rowan Hamilton put forth the quaternions and biquaternions, James Cockle presented tessarines and coquaternions, and William Kingdon Clifford was an enthusiast of split biquaternions, which he called algebraic motors. These non-commutative algebras, and the non-associative Lie algebras, were studied within universal algebra before the subject was divided into particular mathematical structure or types. One sign of reorganization was the use of direct sums to describe algebraic structure. The various hypercomplex numbers were identified with matrix rings by Joseph Wedderburn and Emil Artin. Wedderburn's structure or theorems were formulated for finite-dimensional algebras over a field, while Artin generalized them to Artinian rings. In 1920, Emmy Noether, in collaboration with W. Schmeidler, published a paper about the theory of ideals in which they defined left and right ideals in a ring. The following year she published a landmark paper called Ideal Theory in Ring Bereichen, analyzing ascending chain conditions with regard to ideals. Noted algebraist Irving Kaplinsky called this work revolutionary. The publication gave rise to the term Noetherian ring, and several other mathematical objects being called Noetherian.